All right, welcome everybody. Thank you all for joining us. It's great to see more people joining us in the room, which is wonderful. Slowly we're getting back to normal. But thank you to everyone who's joining us online as well, be it on YouTube or on Zoom. It's wonderful to have you all here. And at the end of these meetings, we also have a chance for some virtual networking as well, for those of you that are joining us online. So today we have the great pleasure of welcoming one of our own, Professor Rais Latypov, who, as you know, is a full professor here at Wits Geosciences in igneous petrology and ore petrology. And he joined the school in 2013 and has been with us ever since. He started off his research career with several degrees in Russia and then did a PhD in Finland at the University of Oulu and joined the staff at that university thereafter. And then he joined us, as I said, in 2013 and has, as you'll see today, been working on the Bushveld as well as many other things related to igneous petrology. So Rais, thank you very much. Welcome, and over to you. Perfect. I'm just going to try to get rid of this. Where is it better if I put it up here? Thank you.
Okay.
So perfect, right?
We keep it.
I'll set it up now.
Okay. Thank you, Grant, for introduction. Okay, I hope it will work. Okay. Once again, thanks for coming, and it's nice that we have some international audience as well. And today I'm presenting on behalf of my colleagues, co-authors Sofia Chisikova, Richard Hortz, Gelo Kostin, and Maurice van der Merwe. And you see this title. And of course, that's going to be a story about the Bushveld complex. Okay, we're not moving for some reason. Again. Sorry. Video. It works. Okay. Okay, sorry for hiccup. Okay, for those who are not familiar, just a few words about the Bushveld complex. I mean, in the audience who is on YouTube. So that is a giant, South African giant with lion's share of all these resources of platinum, chromium, vanadium, etc. So see how many mines, you can see it. So that is simplified map of the Bushveld complex with its eastern, western part, eastern and northern, and we believe that they are connected at depth. So it's a real giant with 350 kilometers across or something, even more, I think. And this cross section from Johann Kruger, I think I'm sure you're familiar with this section. And basically what I would like to say here is that, yes, we know that Bushveld is 9 kilometers or something like that, but we all know, we'll agree, more or less, that it never been as big as 9 kilometers. So that is the body which was growing incrementally. So with numerous magma pulses coming into the chamber, and we see abundant evidence for this process from angle unconformities in the field, from compositional and isotopic reversal between the zone. So we know it never been as big as 9 kilometers. But still, you know, it's the question I was kind of entertaining for a long time. I still was curious to know what was the thickness of the resident melt column at any particular time during the evolution of Bushveld magma complex. For example, the main zone, if you take main zone. Okay, imagine we already crystallized marginal zone, we have lower zone, critical zone, we form all these deposits, and now we came to the main zone. Okay, how the magma chamber looked like at that time? How many liquid was in the chamber? Well, 100 meters, 500 meters, maybe kilometer or much more. It seemed that most of my senior colleagues believe that was below 1 kilometer, but these are all indirect, highly indirect, I would say, estimation. And it's understandable. It's really difficult to get this estimation. Who knows how to do this? And we spent some time thinking. I think we've at least I think, or at least I want to believe, that we found one way to really to do this. And that's what this presentation is about. And I will take you now to the main zone in the Eastern Bushveld complex with almost Shakespeare question, to abut or not to abut, to be or not to be, and we'll see in a moment what I mean. So I'll take you to this part of the Bushveld complex, and it is very interesting part, one of the most interesting from my point of view. Why? Because it is in this area with this thick pile of the Bushveld complex thickness suddenly decrease in thickness and becomes just very thin. So just to introduce some names which I will use. So here in this area we have a city, the town Rusinikal. So I will call this part Rusinikal area. And here we have Belfast. I call this Belfast area. And that step, that is where this is a Tonteldos, and I call Tonteldos step. So in this area, we know that we have spectacular cross-cutting relationship, transgressive relation between the base of the Bushveld complex and the sedimentary rock of Pretoria group. What also we have here, and that is the point which I'd like to make, that's cumulate zone. We see that cumulate zone in this area above the chamber floor. So they terminate again the chamber floor. For example, you see this the critical zone. It stopped here. It terminates, and major part of the main zone does the same, and so that is the what we know, and that was shown in many schematic sections like these. For example, where basically we show here, what's shown here, this Tonteldos step, which I call Tonteldos step, covered by marginal zone. And then all this zone, lower zone, abuts the marginal, critical zone stops here, major part of the main zone stops here. So everything is abutting. And what does this mean, this abutting for the mechanism of magma emplacement? The answer was given by Martin Sharp in his well-known paper in Nature about strong isotope evidence. Basically, his idea that cumulus zones above the floor because the chamber expands upwards, that is a sequence of events, with, and that is important thing, with concurrent crystallization, magma in the chamber. So we're not just expanding magma chamber vertically and laterally, we're also crystallizing at the same time. So we brought some magma here and crystallized main zone, or let's say lower zone, then bring more magma, we crystallize, forming critical zone, etc., etc. And that's why these layers above the chamber floor. So that was explanation. And I would say the explanation is very clear, very logical, and I was very happy about this until one point. I looked carefully at the map by Maurice de Merwe, who is a co-author of our study, and that is a paper in our local journal, South African Journal of Geology. And this is a map. This is a map. It's black, white, and with a lot of details. So we're not usually spend much time looking at this. But at some point, I don't remember why. I looked carefully, and I realized that something is interesting really here. If we look at this, so that is the Rusinikal area, that Tonteldos step, and that is the Belfast. So if we look at the bell in this Rusinikal area, so then at the base of the main zone, we see these three dotted lines. So 1, 2, and 3. So that's three. If they're here, then if we look at the Tonteldos step, the same thing is 1, 2, 3, and even if we go further, we go to the Belfast, we still have these three dotted lines. So what are they? There's not much descriptions, but these are prominent markers, anorthosite marker at the base of the main zone. And Maurice called them lower mottled anorthosites, middle mottled anorthosites, and upper mottled anorthosites. Well, if some strange noise. What is it?
We've muted everyone. There we
go. Okay. I think you you're getting where I'm getting at. So, you know, if now again stop that showing, Grant, I need your help.
Just take that and then go, yeah.
Huh?
I think it should be fine.
It should be one. No, it doesn't move it. Again, we need to restart or no, just okay. So now, okay, then if these markers are real, then the main zone does not actually above the chamber floor. And I'm stressing if. Why if? Because if we go to the earlier papers, earlier studies, and actually there are a lot of studies specifically on this area, and that is the earliest one I found with Grunewald, 1970. So specifically devoted to this area, specific map. There's no north-sides here. There's no north-sides on this map. And then if we go to Priestley and Martin Sharp in the paper 1979, where they studied the tennis ball marker, these guys here, over here. Then again, there's no north-side marker. Then 1985, Martin Sharp, the paper already mentioned, again, there's no markers, no north-side marker here. A detailed study of this specific place where there's a so-called Loess Drift fault. Again, there's no north-side marker here. And even if we go to the final compilation by Molyneux in 2008, there's still no north-side marker. And that's why I got worried, you know, what does it mean? Is this reality or it's a fantasy of Maurits, or what is it? Why none of the maps show there is an north-side there? We got so interested that we even went to see Maurits, to chat to him in Port Alfred. He is, you know, he quit geology a long time ago. He's a dentist, quite successful dentist, I guess. Gets salary much better than, much higher than we have here with his work. Perhaps we're wasting our time here. And what Maurits, fortunately, memory already fails him a bit, but he was clear with his reply to my question. The north-side there, go and find them. I don't care about what other map shows. They are there. And then I remember Paul next told me that Maurits is a great observer. You know, he mapped basically this alone, this northern limb. And we're still using this map. So Paul told me if he put something on the map, it is there. Okay, so with these kind of ideas, we started with Sofia this hunting season for another side markers in this area. And we spent about 6 months or so in this area, looking and specifically at the base of the main zone. And that is finally the map which we produced, to be exactly, Richard Fonsi produced using the data published. And it's quite a nice map now. We have geology overlaying on the topography. So it's very, really helpful and was very helpful in the field. So altogether, we've done here about 7 profiles, detailed profiles. And we start with the first one in this area, in the Rusinikal area. Let's go there. And the first traverse, and it's very nice area here, no people, remote really. And we already found these 3 on our side. They're really there, and they're quite spectacular. And especially the lowest was, the low mount is 57 meters thick, you know, the cliff. Just for those who are familiar with this area, Boysendal mine is somewhere here, Mirensky Reef down there, so far away. And these on other sides is very thick here, and we see the basal contact. And that is when you're walking just the sea of an north side, a north side, a north side, and a north side, with spectacular texture, with a great variety of these oikocrest, you know, and that was specific study, petrographical study of this north side. They're really beautiful, simply beautiful. And you don't need a thin section to see that the orientation of plagioclasts, randomly orientated plagioclasts, and that tells me that there are a lot about the formation of the north side, but it's not today's story for today. And so that was the first. Then I show you one along this Tonteldo step, and the same thing, we have these 3 north sides there. They're really there. And then another one is just right here, right here, where we have where the Bushveld is sitting on Dalston basalts, and at the very base, again, we see these three penoxosites. So it's quite, yeah, you know, you're working several months, but you can tell the story in 1 minute. It's quite disappointing. Well, all I can say that they're here, you know, they're there. So they do exist. So it's not a fantasy of Maurits. He is really a great observer, and that was very interesting thing for us. And so the main zone does not really, the answer is quite straightforward. The main zone does not really abut the chamber floor here. It's not abutting. Then you see this, we've done this section AB, if you see it, ABC, AB, that is where Richard Horsey, using micromine, done a real true section. That is here. So first real one with this lowest drift fault, then there was, and so 11 degrees, and that's real true section. So it's not a matter, it's true section. And then this was reconstructed before this, before that fault. And I think I will have better picture. Okay, that's showing basically what I might show. So what do we have here? We're talking here about the, okay, first of all, about the scale, 0 and 10,000. So that is 10 kilometers, 10 kilometers, true section. So we have here what we call Rusnickel subchamber and Belfast subchamber, subdivided, kind of subdivided by Stolberg remnant. So that is, I'm stressing, that is not a dome, like for city dome, for example. There's no evidence for dome. It's really the just remnant, erosion remnant here, which subdivide these chambers. And then the Tonteldo step, about 35 kilometers, which connect these two subchambers. A low mottled anorthosite, paraxenite marker, and main magnetite layer. So as you can see here, and that's so the true thickness, the true vertical distance between the top of the Stolberg and the base of the, okay, in the base of the main zone, so where we have this low model on the side, this is 4 kilometers. So in other words, these anorthosite covers the entire area. It's everywhere. So despite these 4 kilometers difference between these two subchambers, the anorthosite is still there, the same amount goes there. So that means that in order to blanket this topographic relief in the temporary floor of the Bushveld chamber with igneous layering, like anorthosite, resident melt column must have been thicker than these 4 kilometers. I don't know how much thicker, maybe 5 kilometers or so. I took 5 kilometers. It's because that's difficult now to say really how thick, but at least 1 kilometer more. So that's basically the idea. So to cover these this step and these two subchambers, you need a thick magma column, at least 5 kilometers here, and that's maybe a kilometer here or so. And this conclusion about the big magma chamber, big magma column, also follows from the mineralogical data, not ours. That's a section right somewhere here. Was done by Grunewald a long time ago in the 70s, who presented this, who done a lot of analysis here, and shows nicely that this part of the main zone before the paraxenite marker shows systematic evolutionary trend in N content of plagioclase, evolves in mg number of paraxenes, and that also emphasized by the change in the crystallization sequence. So here we get GABR on the right, then so two paraxene, OPX and CPX are object. Then these are joined by pigeonite. So we have 3 paraxenes in this area, and then pigeonite OPX disappears due to peritectic reaction. We have just pigeonite and object. And a long time ago, I did this graphical analysis to show that that is what we exactly expect from phase equilibrium, such kind of sequence. So, and only at the level of the paraxene arcanite, we have a major influx of new magma into the chamber, which reset everything, and we have these reversals and formation of paraxenites. So it just, once again, it says that these evolutionary trends and crystallization sequences confirm the idea that we have a big mass of the magma here, which crystallizing internally and forming these trends. Okay, to summarize the proposed crystallization history based on that. So showing Russinica, I skipped the story of critical zone here. Start with the main zone, Russinica, Belfast, Tonteldo step. And to form this low mottled anorthosite, we're having about 5 kilometer thick column of the main resident, I'm stressing resident melt column. And then we crystallize, differentiate, and forming this crystallization sequence with the pyroxenes and the A content, etc., forming the main zone. And at some point where we have this main already residual melt, we have new magma pulse coming into the chamber and resetting everything and forming pyroxenite marker. And then above we're forming upper zone from this melt. And Gabi Gelokosten nicely also modeled that, the whole trend using melts and he reproduced the crystallization sequence and mineral composition and everything like that. So that is a picture showing the model for crystallization history, the entire sequence where we're mostly focusing on main zone and stressing how big was magma chamber at that time to explain the existence of these anorthosite markers. Okay, that was kind of basic story. So what kind of implication we may have, we may suggest from these data. I think we have application for that idea about the big magma tank. As you know, there's a lot of decades in the past century. We were pretty happy with the idea, and we're working in this paradigm of big magma chamber, big magma tanks, as a fancy name now. So implying that we had a large, long wave and totally molten magma chamber like this. But now this idea is questioned by several group of researchers about 3 major approach. And just one, I show here only one. Perhaps most popular about the having, instead of magma chamber, having the transcrustal marshy system from the Mocha up to almost surface. And basically all this approach tell us that such magma tanks may not exist or do not exist really. We have either marsh or we don't have anything, just maybe seals or something like that. And look, coming back to the Bushveld complex, if we look now at the reconstruction of the area of the main zone done by Jochen Kruger, and we take into account these numbers which I presented, 1 kilometers, and then we take the area of the Bushveld complex, 100 square kilometers, so that we just very simple calculation, we end up with with the amount of magma at the time of the formation of main zone. It's around 380,000 cubic kilometers. And that is a lot. That is a lot. And of course, it may be less. I actually think it may be even more. But still, we're somewhere in this area. And of course, we talk a lot about this in the media, especially about super eruptions, how deadly they are. And but maybe if we look at these numbers, at these largest ignimbrite tuff super eruption, like 600 Bishop tuff, 600, or the biggest one, 13,000. That's now if we compare with what we assume we have in the Bushveld complex at the time of the main zone, that's all babies, just babies compared to what we have in the Bushveld complex. And that amount of magma is only comparable to estimates of some Earth-large igneous provinces, like if we take the entire Karoo and put in the magma chamber, or Afar, something like that. So that gives us an idea about how much magma we had at that time in the Bushveld complex. So with these ideas, I conclude that Bushveld complex, at least at the time of the main zone, it was a big magma chamber. And I think that traditional approach to the mafic layer intrusion, like a big magma tanks, which was pioneered by these 2 gentlemen who wrote this Bible, layered igneous rocks, and Wager and Brown, and then developed in series of the layer book. I think that idea is not dead, really. It's still alive. We can still happily live with this idea. And I think that's too early really to discard this classical paradigm developed by several generations of igneous petrologists. Rather, rather, I would suggest that we need to redirect our efforts to find out how these new geochronological, geophysical, thermal modeling can be logically reconciled with the classical paradigm. And I think I have some ideas about how we can do this, but I think that's it. And if you're interested to know something more about that we have a preprint now under review, which contain much more information about that study. And I think I'll finish here, and we'll be happy to answer any question if we have.
Okay. All right, thank you very much, Rais. So we have plenty of time for questions with this interesting topic. So let's take some questions from the room to begin with. Do we have any questions in the room?
Oh, no.
Oh.
Okay, we'll begin with Ben.
Yes, Ben.
So we
Just
know,
nice and loud, Ben, for this.
okay. So we know from the strontium isotopic stratigraphy that there's variations in the 87-86 ratio in the lower part of the main zone, and then it's fairly continuous
Yeah.
with the upper part. So how, in the context of a 5 kilometer thick vacuum chamber, how do you explain the varying 87-86 ratio?
Well, you know that's what the variation. They are just above the Mariansky Reef, right? It is basically it starts with it stops at the level of the giant mottled anorthosites. Then it's more or less there, and that story starts with these three anorthosite markers, and I think this lower mark is not the one which we call giant mottled anorthosites. At least the distance which I see in Boisendal area tells me that is different one. So all this variation you're talking about, they are below that area.
Okay, we'll go to Axel.
Yes, Axel.
How does the thickness of these unauthorized markers change laterally from the center of this?
Yeah, I didn't tell that. Of course, we just our style. We're sure that they are there now. So that is the major conclusion. But it needs really very detailed study. We need to find a PhD, postdoc, whoever, to study them carefully. What is really how they change along the strike. What are the composition, isotope, etc., etc. So I think it's very interesting study to do. We know that they're pinching out, of course. The one which I showed, 50, 70 meters, it becomes about 5 meters along the strike. But the point is that is the same, similar, that is the same guy. But definitely we need a detailed study here, and that will be interesting. Bring a lot of new, I think, discoveries.
Yeah, go for it. Nice and loud.
So my question is not directly related to well, it is related to competition, but it's still not because they have become so one thing I noticed was so my question is like if the history they will include interpretation. What is there are still inconsistencies in the definition when we say because the fact that in some ways they include and some they don't. So it's the history consistency.
Well, that's I see your point. It's a very different question. Royberg's story. Royberg sitting in this Belfast subchamber. So Royberg, they're sitting below and above. So the intrusion is sitting in between this. We've called Dahlstrom also. But the relationships, that's not my area yet. Also, I find very interesting things, I think, in the field with the Dahlstrom vessels. Very fascinating. Yes?
Can you comment a little on that Tonteldu step?
Yeah.
You're saying that was a pre-existing topography. How certain of that are you?
Yeah, it's not that I'm saying pre-existing topography. The chamber formed somehow, and that is a totally separate subject. You know, how to form this chamber. You know, it's a big question. I'm sure if Alan wasn't here in the audience, he will ask me now how you explain it. I don't know. I don't know. In a simple way. But I can say that from field observation, what I see above, below Bushveld, it's funny that and nobody can answer me this question. It looks as if all these rocks, which were sitting, which were at that place where we have Bushveld, they disappear. I don't see evidence for the dropping there below. I see it on them up, they just disappear. And that's something which really puzzled me. I don't know.
So there is a seismic line kind of in that general area, which I think, you know, Stephanie is working on at the moment.
Okay, I'm not familiar with.
It's worth. It's very confusing.
Okay,
So
just like yours.
I think it will offer some more interesting questions.
I can
and then
check.
The question on the age of the lower Midland, upper model and orthosite markers I want to ask in terms of cooling, would they have reached the same temperature at the same time?
Reach the same temperature at the same time. You know, they're not that far from each other. So
the thickness changes dramatically.
Yeah, thickness change dramatically, but still 55 meters along the strike, and they're still at the base. So I think that in terms of that reversals you're talking about, I don't think it's resolvable. It's still, I think in one, they will be in one area, sitting all of them. So unlikely you will find difference between them. I think so. But that requires separate study, really.
Okay, it looks like we have a question from Lou. So please come through, Lou. You can unmute.
Okay, thanks for the talk, Rais.
My pleasure, Lou.
My question is, how do you account for the fact that in the northern limb, the composition of feldspars in the main zone is basically very constant for thousands and thousands of meters, which is very different from the picture you illustrated for the eastern limb?
Actually, I had the same question to you, Lou, when I was, you've done your job with Freddie almost 25 years after his work, and in your paper, which I read recently, there's no any word about that. Why this you came to totally different evolution trend in your study, and why is this so? Why in that part we have this change, systematic change in N content? Why in your study it seems that you don't have? Although I recently talked to Freddie and look at his data more carefully, and I think I see the trend there. I may be mistaken. We need to look carefully, but I think it's not that clear, visible as in this part. But I think you still have this trend of decreasing N content in your main zone in the northern Bushveld as well.
Okay, thank you for that, Lou. And then let's see, here we have a question from Alan Woodrow. Do you consider concurrent country floor uplift in giving rise to the height variations?
Concurrent country floor uplift. No, Alan, we don't see it. We don't take into account, because looking at the stratigraphy, which we see in this, in what we call Stolberg remnant, there's no evidence for that. At least we don't see it. It's just normal layering as everywhere, and there's no deformation there, no evidence for the uplift. Perhaps we need to look more carefully, but that's our impression.
Okay, do we have any other questions from the audience here, or anyone want to raise their hand and come through? But we have a question from Linda at the end, Rais, which I think is a good conclusion question. What is the implication if the main zone abuts or doesn't abut?
Yeah, the major implication for the thickness of the main zone, and then of course the size of the magma chamber. Because if it's a butt, then it can be growing in. It was still growing incrementally, basically. But the point is that in our case, it was growing and it was not crystallizing. So the magma pulse coming to the chamber must be keeping it away from crystallization, growing to the big magma chamber. So I think it was something else.
Yeah, we have one last question from Gillian Fulger. Gillian, please unmute and join us. Thank you.
What was it before? Nothing here.
Gillian, we can't hear you, but you are unmuted. Maybe a microphone problem.
About that. Can you hear me now?
Yes, now we can hear you. Thank you, Gillian. Go for it.
Thank you very much for that really stupendous talk, eye-opening. I'd like to ask you, is there any geological evidence that such giant reservoirs of magma could exist at the present day?
Yeah, thank you. Yeah, it's a good question. And actually, that's, I mentioned about geophysics. So how to reconcile that? Geophysics tell us that they do not exist at the moment. And on this basis, they say that they do not exist. At least petrologists take it as evidence. My feeling that if you look at the late intrusions, then the time between the formation, million years, 10, 20, 30 millions. So basically with the current data, we are looking just at seconds in the history of the Earth. And I don't think on the basis we can argue that these magma chambers do not exist at all. Short question, I'm not aware of the geophysical data about the existence of such a big magma chamber.
I would just like to mention that in my view, there is significant geophysical evidence that such magma chambers must have existed, throughout long periods of time. And
really?
Yes.
The world geophysicists tell me the opposite.
Yes, well,
I'd like to get your references if you can. We'll be very.
I would be very pleased to share with you the materials that I think indicate to us that there's no other way, but such chambers must exist.
Yeah, we'll be happy to get these references.
Great, fantastic. We'll just go through the chat quickly. Gillian does ask if you can send her the link to the preprint, right? That would be great. And I think that's it. So thank you. Oh, there's a last comment from Alan Glasner.
I'm sure.
Here we go.
He is coming in one month to talk here.
So I think everyone can see this, but just to repeat for those people on YouTube, there is no geophysical evidence for shallow, melt-rich magma chambers, even small ones, at the present day.
Yeah.
And if you want to know more about that or continue this debate, then Alan is kindly giving a geotalk on the 24th of March.
Yeah.
So same link, same time, on the 24th of March.
I should say that I'm very grateful to Alan for challenging me with the questions. That because of him, I started modeling the erosion, now the paper. Now we've done paper on Sudbury, on Skergat modeling, etc. So thank you, Alan. You're a very good guy. Also, I disagree with you completely.
So tune in for more interesting discussion on the 24th of March. Yeah. So thanks everyone for joining. It's been great to have you all here, both online and in person. And thank you, John Hancock and CCIC, for the drinks and chips. If you want to partake in the drinks and chips and you live in Joburg, then come and join us in this room every Thursday. And next week, we'll be listening to Axel Hoffman from the University of Johannesburg, who will speak about new views on old rocks. The Dominion Group of South Africa. So Axel, we look forward to that, and we'll see you all next week. Thank you.